So we started. Yes. Okay. So we'll start now. Okay. So we were the last class. We were following Cheng, and today we'll again cover some topics from Cheng, which is single stub and double stub matching, and basically the impedance matching things. I have covered examples from Cheng. So there are also examples in Pozar. So, since we have not discussed these, you can take a look at them by yourself. So you'll be able to, and you can try solving it. You'll be, if you are able to think and like follow questions from Pozar after discussions from questions from Cheng, then we can you can assume that you have understood the question. If not, if there are doubts from Pozar, then we can discuss them in class as well. So we are here now in module 6 doing impedance matching and tuning. We'll finish this today and then we'll start with microwave resonators today. We'll look at series RLC circuit and then the next class at parallel RLC circuit and other topics. So a couple of modules left ahead. So we'll try to finish them quickly. In the last class, we did L section for the impedance matching that is using lumped elements. Then we discussed quarter wave transformer that we already had discussed in some classes earlier. We also looked at the Smith chart technique for L section and quarter wave transformer, and then we discussed this single stub matching example and the method. And we also so we did this using Smith chart. So in Pozar, there is the analytical technique is also given, but since it is complex and not very feasible, so since using a Smith chart is much easier. So I have not discussed that in the class, but if you are curious, you can look at the single stub matching analytical method from Pozar as well. So we'll start with a quick recap of the quarter wave transformer. So we had discussed the L section matching in the last class along with the Smith chart. So if there is any doubt in the Smith chart, please let me know. So we had discussed that quite well in the last class. So for the quarter wave transformer, we had already seen this formula earlier. So we are using this formula to solve to match to match impedances R naught and RL. R naught and RL we are matching, and to do that, what we do is we take the product and its root, and then the value that we get is the value of the impedance that is impedance of the transmission line that is to be put between these two impedances. So we looked at one example where we had to match this 50 ohm line to RL1 and RL2 such that both of them receive equal power. And to do that, we the question becomes first a power divider between these two loads. So this 50 ohm should be distributed into 100 ohms each, and then once we had 100 ohms over here, then we calculated a 64 by using 64 and 100 the value for R10 dash uh, uh, and R20 dash. So this is how we did the first question. Then the second part was to find out the uh, reflection coefficient and the VSWR, essentially the VSWR, and to do that we needed the reflection coefficient. So we calculated that as well. So these are the formulas that is already known to us. Now we discussed the single stub matching. So for the single stub matching, what we are trying to do is so the single stub matching. Essentially, we're trying to match this load over here with the with this characteristics impedance this transmission line. So to do that, one method is that so the earlier methods by using for example the quarter wave transformer that cannot be used for uh, if this particular load impedance is complex. So quarter wave transformer only works if the load impedance and the characteristic impedance of the transmission line, both of them are are real. So essentially, what will happen is we are taking root of two numbers, right? This R naught and RL. So if they are both of them are not real, they if they have complex parts, then this root will give you some complex value, and then again you cannot design a transmission line with characteristic impedance with complex value. So for this case, we use single stub matching. So this particular ZL can be of A plus JB form, and what we uh, what we are trying to do is that we have this distance between the uh, load impedance, and after some distance we add this stub over here. This stub will so over here you can use a short circuit or an open circuit stub. We usually prefer a short circuit stub, and by the short circuit stuff basically gives you some impedance of GB form. And what we try to do is that this A plus JB thing is and this particular length over here gives us some value of the impedance over here, and this value we try to make it of the form 1 plus JB, and then we try to give model this as minus JB, such that at this particular point the impedance that we are looking at is 1, and we are over here when I'm saying 1, it is basically the normalized form. So this capital ZL can be written as small ZL. Small ZL can be of A plus JB form, and then while translating from here to here, this becomes 1 plus JB form, and this minus JB subtracts this part, and we get 1 over here. So this is the idea of while using a single stub. So let's quickly look at the equations that we had in the last class. So essentially we have this capital YI over here, which is the input impedance when you're looking from here, from the from this transmission line towards the load, and the stub as well. And the impedance looking towards the stub is Ys, and the impedance looking towards the load is Yb. So these are the essentially, since okay, so these are all the admittances, and this admittance and in parallel, when you're looking at impedances, this would be Zi 1 by Zi is equals to 1 by Zb plus 1 by Zs. But if you're writing in terms of admittances, then you can just flip them and you can directly write this. Okay, so and you can now normalize them. So now by using R naught, so R naught is equals to 1 by y naught, and then we can normalize this, and the idea is such that this yi should become equal to y naught. So once after normalizing and with our goal to make yi equal to y naught, can write this equation over here. So yi becomes 1, yb becomes small yb, and ys becomes small ys. And yb over here is so this is r naught yb. So if we denormalize it, and similarly this small ys is equals to r naught ys if we denormalize it. So since the input impedance of the short circuit stub is purely susceptible, so if you remember the formula, Zn is equals to Z naught ZL Z naught plus ZL tan something divided by ZL plus Z naught tan something like this. So if this uh, okay, this was something J something, right? Yeah. Yeah, something like this. So this if this ZL becomes okay, this was Z naught ZL maybe. Yeah, ZL naught. So if this particular ZL becomes zero, so this sums becomes zero, and this entire thing becomes imaginary. This J something form. So this stub will offer only uh, this stub will offer only imaginary admittance over here, imaginary impedance, and hence imaginary admittance. So so this particular stub only acts as imaginary part. So the so hence what we have to do is we have to somehow make the real part 1 over here, by using this distance. Now, so this will offer only something of JB form, and this and we and to match this, we have to make 1 plus JB form over here, and we and okay, and so let this B could be minus or plus anything. So for convenience, we are using minus term over here. So the next goal is to make YB 1 plus of YB of 1 plus JB form and YS of minus JB B form. Okay, so this is the goal, and our objective is now to find length D, this particular length D, such that YB of the load section looking into the right of terminals BB has unity real part. So our goal is to find out D such that A plus whatever JB becomes 1 plus JB. So A has to become 1, and the next goal is to find length LB such that the stub required cancels in the imaginary part. So and next is to find this L such that this its admittance cancels the admittance of the this load as seen over here. And to do that, we have these steps listed over here, which we discussed in the last class using the example. So let's quickly look at the example. So the question had there is a 50 ohm transmission line connected to the load, and its impedance is and the load impedance is also given over here. And we have to find the position and length of the short circuit stub. So we are using a short circuit stub. There is also an open circuit stub example in Podzar. You can take a look at that as well. So in that case, what will happen is that we have P short circuit over here and we have P open circuit over here, and you have to calculate the distances of either from this or this point. So that is one major difference between the problems having open circuit stub and short circuit stub. So we have R naught given over here, we have ZL given over here. We can normalize it. Once we have the ZL over here, we enter through ZL at point 1, and then we can make this OP as taking the OP as the radius. We make this particular circle. We make this circle over here, and once we have made the circle, we mark the point to this. So this we entered as ZL. We now calculate the admittance YL, the normalized one, and we mark this point P2 over here, and note the value of over here as 1.9. Now and that too in gradient towards generator part. Okay, so starting from here, this is 1.09, and next thing that we do is we draw this G equal to 1 circle and see where these two circles intersect, P3 and P4. P3 and P4. So what is happening is we have admittance value over here. So this admittance is of whatever form A plus JB form, right? And this circle has G real part as equal to 1. So once we are moving from here to here, or from this direction to P4 over here, what is happening is that we are making A to 1. So the first goal was to make this as 1. Okay, and we have some imaginary part as well. So so the first thing is done. We have made this A equal to 1, and now we are concerned about the imaginary part. Now okay, so we have done till here, and now what we do is that once we have reached this point over here, so we have the imaginary parts with us. So the value of this imaginary part gives us 1.2. So this can be plus 1.2 or minus 1.2. And regarding using these values, we can uh, mark this as 1.2. So this is the plus 1.2, and this is the minus 1.2. Yeah, this is the minus 1.2. And this is the plus 1.2. So we mark them. We calculate the distance from here to here, or we calculate the distance from this P short circuit to this entire distance over here. So remember, we are since we are looking from load, we will go from load to generator. So the clockwise direction only. So we starting from here to here, starting from here to here. So this gives us two lambda values. Okay, sorry. So these are the two values over here. So this is the JB2 form of value that we calculated, and for the and for the distance that we had moved from the d distance, right? For the d distance, we have to see. So we moved from P2 to P3, right? So we move from P2 to P3. So this value over here, so we can calculate the distance from P2 dash to P3 dash. So this distance gives us the value of d, and similarly we move from P2 to P4. So we calculate the distance from P2 dash to P4 dash. So this entire thing in the direction of the generator. So this is the another value for d. Okay, that's how we get the two values for d. And once we had to get rid of this plus j 1.2 or minus j 1.2. For that we see what this particular line. So this is 1.2, right? Yeah. So this is 1.0, and this is 1.1, and this is 1.2. Yeah. So this is 1.2 plus 1.2 over here and minus 1.2 over here, 1.2 over here. Yeah. So this is the example. So we'll start with what the material for today. Um, uh, okay, maybe I can pause over here and let you uh, see this. And if you have any questions, you can ask. So we had discussed this yesterday as well. So I thought maybe it will be a good idea to discuss this again, because Smith chart is usually daunting at the first instance. Like it's usually seems complex, but once you get a hang of it, you will understand. Okay, so if there are no questions, we can start with the material that we are supposed to cover today. So up till now, we looked at single step matching, but the single step matching had one issue that okay, let me just draw this again. So what is happening is that when we are so we have this some load over here, and we are introducing uh, we're calculating this d distance, and then we are introducing a stub over here, and this stub has some length. But in doing so, what happens is this particular d can be we might end up with this d with such a value that that is not comfortable for us to add a stub over there. For example, if we have a very small PCB with a number of traces going at some places, and we somehow we are trying to match this component to this value, and we might end up with this particular distance has some place that it does that there is another trace running next to it. So we do, and there is another trace in this direction, so we cannot add a short circuit stub over here or whatever length this is coming. So right. So but it might happen that this trace bends over here and this trace bends over here, and we are comfortable with having, we can add a stub over here. So to get this flexibility, what we can do is we can use this particular uh, method called double stub matching. So over here, as you can see, there are two stubs, and by using this first stub over here, we can manipulate this distance d naught over here, which determines the distance between the two stubs. And usually it is of best interest that we take this as lambda by 8, or uh, lambda by 16, or 3 lambda by 16, or like you get the idea, right? So we this is a good idea if we are if we use this lambda by 8 lambda by 16 value. So so this will become clear when we look at examples, why this is better. So okay, so the method of impedance matching by means of a single stub described in the preceding subsection uh, can be used to match arbitrary non-zero finite load impedance. So single stub was well and good, but again this required us that the stub be at a specific point, and this also changes with the value of the frequency, because right we get the distance in terms of something lambdas, and depending on the frequency which we are matching, this particular point, this where the stub is to be attached, will change. Now practical difficulties are happen when uh, this point where the stub has to be added is at an undesirable location from a mechanical viewpoint. Okay, so like in theory, you must have you get a distance this d, and this is all right. This could be very small, very large, whatever. But while fabricating the prototype, you might find that this particular d is not right for the particular design that you have already made. So in such cases, we introduce this technique called the double stub matching, where we have two stubs, and so when once we have these two stubs, we have to calculate this LA, LB, and this D naught. But as a standard practice, this D naught we decide like beforehand, and then based on this D naught, we calculate this LA and LB. Okay, so we'll look at an example, and this will become more clear. But do not worry if you don't get this at the first instance. So this will require multiple readings and solving several questions, so that you get a hang of it, so that you can solve new questions, especially during exams. Okay, so just we have already seen about the arrangement. So essentially, the arrangement is such that we have this junction over here, A dash, and we have another junction B dash, where the two stubs are being attached, and the length of the two stubs are given by LA and LB. And just for nomenclature, remember this is YI is the input impedance, final input impedance that we that has to be matched with R naught. So okay, and looking from this point to towards this direction, the admittance that we're looking at we get is YB. Similarly, the admittance looking at the first stub is YSB, and at the admittance looking at the second stub is YSA, and YA is the admittance looking in this direction from this point over here. Okay, and similarly. And remember that the characteristics impedance of these stubs are all R naught. Okay. So this is all, and the distance between these two is given by D naught. Now the final goal is to match this yi with R naught. Okay. So once we have so this yi is we have to match this to yi to y naught, which is equal to 1 by R naught. So the R naught is equals to 1 by y naught. Uh, and this and the admittance at this junction over here can be given as the sum of YB and YSB. So YB is the admittance seen over here, and YSB is the admittance seen towards the stub. Again, since both of these are short circuited, they will only offer the admittance will be purely imaginary. The admittance will be imaginary offered by them. So, and in terms of normalized admittances, so this yi will become 1 because this has to be equal to y naught, and this yb and ysb will become small yb and small ysb. And now again, the same thing happens as we saw in this single stub matching. Since this particular this stub will only offer imaginary impedance, so we have to make sure that the real part b dash is equal to 1. So whatever happens, this has to become 1 by jb form, and and we can cancel this jb by making this stub as minus jb. Okay, so this is all that this is till here. Everything is same as the single step case. Maybe I'll pause over here, and if you have any questions, you can ask. Else we'll move forward. Give you a minute or two to look at this line. Okay, so we'll proceed. So we have seen that we have at BB dash. So this is at BB dash. We have the admittances as yi equal to yb plus ysb, and yi has to be equal to y dash by z y naught. And if we normalize it, we get 1 is equals to yb plus ysb, and we have to make sure that yb is solved to be of the form 1 plus jb, and we then we make the ysb equal to minus gb. So this is our objective. So again, remember uh, the Smith chart that we have to use the admittance Smith chart, and on the admittance Smith chart, the point representing YB must lie on the G1 circle. So if you remember the Smith chart, so the Smith chart looked something like this, and we had more circles over here. So this the point representing this YB must lie on the G1 circle. So we have to make sure that somehow the YB point should come will have to be evaluated, will must lie on this circle over here, because this circle is G equal to 1, and this implies the real part of YB is equal to 1. Okay, so this YB will lie on the G equal to 1 circle, because the real part is 1. And this requirement is must be translated by the distance d naught by lambda wavelength towards the load. Okay, so these texts will make sense once we have actually solved the example. So maybe I'll just skip it instead of discussing this now. So maybe let's first look at the problem, and then we'll back to this. So okay, maybe I can give you a quick idea of how we'll solve the problem by using these points. So if you take a look at the circuit over here, and let me just draw this circle over here. So okay, so this is somehow the Smith chart. Okay, bear with me. This is the Smith chart, and this is the G equal to 1 circle. Okay. Now the circle has to be rotated counterclockwise by d naught by lambda wavelengths towards the lobe. Okay. So the thing is, this particular circle is corresponding to this point over here. So at BB dash, we just so I'm giving an empirical idea that whatever happens is that with this YB should lie the YB should be of the form 1 plus JB form, right? So this YB will lie over here. So this YB should lie on this circle, and the circle it is corresponding to this point. Now we have to move this particular circle in the wavelengths towards load. So wavelengths towards generator is in this direction, uh, and wavelength toward load is in this direction. Okay, so it is counterclockwise, and we have to move d naught times. So here this is where we decide that how much should be the d naught thing. Okay, so earlier I said that this could be lambda by 16, lambda by 8, 3 lambda by 16. So these values actually help us in rotating the circle in at specific angles. So if we choose lambda by 8, this will correspond to 90 degrees, and it will be easier to just rotate the circle by 90 degrees. So if we choose d naught as, for example, lambda by 8, this circle we can translate it in this direction. So the circle will come over here. And now, so this circle corresponds to this junction A dash. Okay. So we shift the circle over here, and then we plot the value of ZL. So we will enter the value of ZL, for example. So we come from ZL, we'll find out YL. Small, we will normalize this and then find out YL. So this YL will be some GL plus JBL point, right? So this could be here. So we enter this Smith chart over here. So before entering the Smith chart, we first made the G equal to 1 circle. Then we will translate the circle towards the load in this direction by using by the angle d naught by lambda. So then we'll choose the d as 1 by 8. Okay. Sorry, d. Yeah, by yeah, we'll calculate the this, yeah, 1 by 8 pi. So this will come out. Yeah. So if we choose lambda as lambda by, as lambda by 8, so this will turn out to be 1 by 8 pi something. So this will be something 90 degrees. Okay, 2 pi. Sorry. Yeah. So this will turn out to be lambda by 2, and this is, sorry, pi by 2, and this is 90 degrees. Yeah, just so choose a value of d naught and rotate the g equal to 1 circle. Enter this Smith chart at YL, and once we have entered this Smith chart, this YL has some real part, right? So first we have the goal is to make this real part equal to 1. So we have to make this equal to 1. So we take this YL point and move along the move along the constant imaginary path, which is something like this. And wherever this intersect the circle over here, we choose those 2 points. So this will intersect at 2 points. We will choose these two are the two values that we are getting over here. Okay, so we have reached over here, and we have uh, so the value was over here, and then we made this value equal to 1 for here. Now since we okay, so we made this equal to 1. We have reached over here. Okay, so this was YL, and then we entered over here, and then we made this equal, and then we found out the value due to this stub. And then from here we will since we had moved d naught by lambda times, or that is lambda by 8. So we plot these points. We just take this or at the origin we make the center, and then we cut these 2 points on these circles over here. So then each point will correspond to some value over here, and once we have these two values, we have actually made we have reached the g equal to 1 part, right? Yeah. So we have reached g equal to 1. So this real part becomes 1, and now we are just concerned about JB value. So this JB value is the only term, and for this we can find out the length from the outer part of this Smith chart and get the value. So maybe this became a little complex over here. So up till here, this you must do, and we'll look at an example which will follow these steps, and maybe you can look at a few more examples from textbooks, and then this will become clear. So maybe I'll start with the example, and then give you some time to understand. So so we have a problem. Where the transmission line's characteristic impedance is 50 ohms, and we have a load impedance of 60 plus J80 ohms, and we have to use a double stub tuner spaced an eighth of a wavelength apart. So this is lambda by 8. Okay, So we have D is equals to lambda by 8 used to match the load as shown in the figure. Okay, so so the figure was in the previous slide. Find the required lengths of the short circuited stubs. So we have two stubs, right? So we have to calculate LA and LB. The first step is to normalize the ZL and find out the admittance. Okay, so 1 by small ZL is R naught by ZL, and we have this as YL. Okay, so we have found out small YL. Now the next step is draw the G equal to one circle. So G equal to one circle is over here. So I've drawn this G equal to one circle. Okay, so the G equal to one circle is over here. Next, we rotate this G equal to one circle by 1 by 8 wavelengths towards the load. So this is, if you read carefully, this is wavelengths towards generator, and over here you'll read this to be wavelengths towards load. Yeah, see, load is written over here, and the arrows in this direction. So we'll rotate this one by 4 pi by 8 or 90 degrees. Okay, so if we took this some other distance, then this particular circle would be at some awkward angle, and we will find it difficult. So it's easy to rotate this by 90 degrees. Just take this as the origin, and just you have the mark over here, and then just maybe draw a line like this, take the center and just draw a circle. It should not be much difficult. So we have rotated this circle in this direction. So this is lambda by 8 direction. So we have reached over here. Now we enter at this Smith charted YL. So YL is being plotted as PL. So we enter Smith chart over here. Now notice that this is the real part is now 0.3. So this is at 0.3, and at 0.3 you just make a circle. You can also skip making the circle and just mark directly the points on this Smith chart over here, but if you make the circle it will be much clearer, although you will have more construction lines. So whatever is more comfortable to you, you can make this. You can just highlight the circle. It is which is there. For 0.3 we mark the point PA and PA1 and PA2 at 4. So we've got this point. Now what? Since we had rotated this our circle by lambda by 8 thing, so we translate this particular PA point to PA1 point to PB1 and PA2 point to PB2. So we bring them back over here. So that is done in the next step. So okay. So once we have marked PA1 and PA2, we can read the values at PA1 as 0.3 plus J2.9 and YA2 as 0.3 plus J1.7. So these are the admittance values at PA1 and PA2. So from PA1, we'll get PB1, and from PA2 we will get PB2. So we just take the PA1 and just draw a circle, keeping the compass at this origin. Just make this arc, right? So you will get you will reach PB2 PB1. Similarly, if you just take this as the radius and draw the arc, you will reach PB2 from PA2. So we have PB1 and PB2. Read their values as 1 plus J 1.3 and 1 minus J 3.5. So you can see we have finally made the value of YB real part as 1, and then now we have JBB, this the imaginary part to take care of. Okay, so to determine the length of these stubs LA1 and LA2, so if you remember, we had two stubs, right? One stub over here and one stub over here. So this was LA1, and this was uh, this was LA and this was LB. So for each stub, we get two values, LA1 and LA2, and similarly LB1 and LB2. So for this, the stub which is attached directly to the load, we'll find their values. So we have if you look closely, if you read the values of ya1 with and minus yl, so yl is over here, and we have ya1. So we have ya1 over here. If you read if you take the difference, so the amount of imaginary part we had to uh, add, that was 0.69. Okay, so this particular the distance between, so the imaginary part. So because we were moving on the constant r value, so the imaginary path we were changing, right? So if you read the value over here and read the value over here, so and take the difference, this will come out to be 0.69. Now similarly, what for ya2, the this particular value over here, you read the admittance value and subtract this with yl. So essentially the path of the imaginary path that we had to travel. So this will come out to be j2.5. Okay, so we have got the imaginary part values, and now corresponding to this j 0.69, you find them on the outer part of the Smith chart. So if you take a close look, this this will come out to be, yeah. So this is zero. This is zero over here. This is 0.1 maybe. Some can't read properly. Well, 0.1, 2, 3, 4, 5, 6, and this is 7. And just before 7, we have 0.69. Okay, so we reach A1 over here. At point A1, and at point once you have reached this mark this point over here, you just calculate the distance from the short circuit point over here. So PSC is over here, and remember since we are moving from load towards generator, so we have to cover this entire path. Okay, so this entire path has to be covered. So from short circuit point till here, this is actually 0.25, and the distance from here to here is 0.096. So we add them and we get the value of L1, LE1. Similarly, if you take the value of J 2.15, so we find this first 0 J 2.15. For J 2.15 will be somewhere here. Okay, so so 2.15 will be over here. So we mark the point A2 over here, and then we calculate the distance between the short circuit to A2 value over here. So we take this entire path. So this A2 is actually 0.181, and this from this point from over here. So this is 0.181, and then we have 0.25. So we add them, we get 0.431 lambda. So we have found out the two possible values for LA1 and LA2. Similarly, now we have to find out the value of the length of the second stubs. So if you remember, then we have already made y be equal the real part as 1. The imaginary part has to be taken care of by the second stub. So this reads to be j 1.38 and j 3.5. Now similarly, we'll mark the point v1 and v2 on this Smith chart. So v1 is b1 is found to be over here, and b2 is found to be over here. So you just read the imaginary part values. It is written on the corners. So this is so let me. Okay, this is very small, so I cannot read this now. If you have a bigger Smith chart with more clearer picture, you will be able to read this better. Yeah, so this is 1. This is 1.2. This is 1.4. Maybe, yeah. So the one of the values is 1.38, right? Very close to 1.4. So if you mark this very closely, you will get b1 over here. So once you have got b1, now you have to calculate the distance from the short circuit point towards the generator. So this full its entire length is 0.25, and if you read this value and if you read this value, this is 0.350. So subtracting, and then we get this length from here to here as 0.1 lambda. Similarly, we will do it for B2, and we'll get the length of the stubs for the second stub, which is away from the load. Okay, so this is the way we will solve a double stub matching problem. Maybe I'll just pause over here, and you can ask if you want me to repeat this again, or if you have any specific questions from any particular step. Okay, so if most of the questions, yeah, maybe um, this was too much for one go. So you can read this question. So this is from Cheng. This is from Cheng, and um, you can refer to the textbook and go through the question yourself. So and maybe listen to this recording later along once you read through the text as well at your own pace. I'm sure you will be able to follow this. So this is actually a lot of step, but and I discussed it very quickly. So if you face any problem, please ask me. So I've discussed all these steps in detail. Uh, yeah. So this is just try to look at this particular problem. You will get the idea, and on the similar lines, all problems like this can be solved. You can also refer to Podzar and the questions in the examples in them. So with that, they'll help you get a clearer idea. Okay. So that's all that we are covering from the impedance matching. So there are a few more few topics. This is all from Cheng, and from Podzar you'll find few more topics. You can read them all your own. So we have discussed all the narrowband techniques. So there are some wideband techniques present. So this will you can there's one important one interesting and very popular uh, theorem there, which is called multiple the theory of small reflections. Yeah, small reflections. So you can give it a read, and then based on this, there are some matching techniques. For example, the uh, tapered uh, technique, multi-section. So these are some wideband techniques for impedance matching. So for the theory for multi-section you can read. Tapered is a little complex, but yeah, if you have time and if you're curious, you can go ahead with this. And there is another topic, so we can come back to this, which is Bode-Fano. So maybe we'll discuss this again in the filtering and matching. Yeah, for the filters, maybe we'll discuss this, and we'll at that time only we will discuss it for matching circuits as well. So this is essentially a theorem which discusses about how much matching you can achieve. So this is good to know. So you can give yourself you can give us some time, go through these examples, and also look at small reflections, multi-section matching, tapered lines. If you feel like it, this is something practically that we use on PCBs. and also give this Bode farmer. So that's all from this particular module. So we're finishing up with the impedance matching module. We'll start with microwave resonators. Uh, Microwave resonators are used in a number of applications, including filters, oscillators, frequency meters, tuned amplifiers. So they are very important. So they, for almost all designs that you do, you must we usually calculate the resonance frequency, and this helps us and solving a lot of problems and deciding where the resonance is happening in the circuit. So this is very important. And since this resonator, microwave resonators, they're very similar to the lumped element resonators. So when I'm saying microwave resonators, we're talking about distributed elements. Okay? Uh, these distributed elements, but their effect is same as the lumped elements. So we'll discuss the series and parallel RLC resonant circuits, and this will give us a very good idea of how the microwave resonators are working. So maybe for the sake of brevity, we'll discuss these series and parallel, and quickly go over the different kinds of microwave resonators. So we won't detail the theory of the distributed elements. You can take your time, and so because this will take some time to go through this. So we'll discuss the series and parallel RLC resonance circuits. So today we will look at the series resonance circuit, and then in the next class we can look at the parallel resonance circuit. Okay. So this is a simplified series RLC circuit. So we have R and then C, uh, essentially making up the RLC circuit. We could have multiple R's and multiple L's and multiple C's. We can take the equivalent values, and that's it. So to calculate the impedance, input impedance of the circuit over from looking at over here. So this turns out to be R plus j omega L minus 1 by j omega C. So it's very straightforward. So whatever we will look at now, we'll go over it quickly because this is something that you must have already covered in your network theory or class 12 physics. So for power delivered, so we know that the it is given by 1 by Vi conjugate, and then this we can also write this in terms of the input impedance, and input impedance with current, voltage, and substituting the value of the input impedance. So very straightforward. So we have we can write down the input impedance, the complex power delivered, the power dissipated by the resistor, the magnetic energy stored in the inductor, the electric energy stored in the capacitor. So this is given by We, Wm, power loss, and then so Vc is over here is the voltage across the capacitor, and we can write the complex power in terms of the power across the power dissipated by the resistor and the energy stored in the inductor and the capacitor. So this is the expression for the complex power. And we can also write the input impedance in terms of the power, so which is uh, by this form over here. So we had the power. We have taken this expression, okay, like this term and this term over here, and we have just written the power in terms of we have written the input impedance in terms of power and the current. Okay, so this is the expression for the complex power, uh, where P loss is by the resistor, magnetic energy by the inductor, and the electric energy by the capacitor, and the input impedance in terms of the power loss. Okay, so for resonance, the resonance will occur when these particular terms becomes zero. That is, the imaginary term becomes zero, which will happen when the magnetic energy stored in the inductor will become equal to the magnetic energy stored in the capacitor. So when this happens, the input impedance will be so the imaginary part is lost. So this is just P lost by half I square, and this is equals to the resistance. So this is purely real, and omega m Wm equal to We implies that the resonant frequency will be given by 1 by root LC. So if you may equate these two terms, so this will be end up with these two terms, equating these two terms. The 1 by 4 I square will cancel, and we will get omega square equals to 1 by root LC at omega naught. And another important parameter, so you must have already read about this, called the quality factor. So quality factor is defined as the average stored energy divided by the energy loss, or we can also write this in this way. So the total energy is omega m plus Wm plus We, and the energy lost is across the resistance. So the quality factor is actually the measure of the loss of a resonant circuit. Okay, so lower loss implies a higher Q. So you can see over here, if we have lower loss, we will have higher Q, and this loss could be due to conductor, dielectric, or radiation. So fairly straightforward. So these are the different kinds of losses. So very similar to the kind of losses that you see in either antennas as well. So all these losses are like captured by the resistance R. Okay. So whatever, so you can use individual notations for this, but all of them are being captured by R, which is covering the P loss over here. And if you add any additional connecting network, so that will also include to the losses on the circuit. So all kinds of losses will affect the Q and will lower the Q. Now there is, so if you have a particular circuit, for example, the circuit over here, uh, so, and if you want to know the uh, quality factor of just this network over here, irrespective of anything else that is attached to this network, so that particular Q is called the unloaded Q. And if you attach any more element to this, then the total Q will for the circuit is called the loaded Q. For example, if you add any load resistance over here. So for a series resonant circuit, the unloaded Q can be evaluated as 2 omega m. So essentially, for at resonance, this omega m will become equal to Wm will become equal to We. So this 2 Wm omega naught by P loss. So just writing this as 2 Wm, which so this essentially becomes equal to L by R. So we substitute the value of Wm and P loss, which is all some half I square by R and half Li square. So just cancelling these terms, so you get omega naught L by R, or also which is also equal to 1 by omega naught RC. So this is the unloaded Q expression over here. So this shows that Q will increase as R decreases, and R is represents loss. Next, we'll consider the behavior of the input impedance Zn. So one more thing to look at. So maybe I'll pause over here, and if you have any questions regarding this, what we discussed. Yeah. So we discussed the previous slide. We had discussed the input impedance, the power dissipated, the energy present in the inductor capacitor, and the dissipation across the resistor. So all the expressions for that we have already seen, and over here we maybe some of you might be looking at Q, the quality factor for the first time. So if you have any questions regarding this, you can ask now. Else we'll proceed a few more a couple of slides more, and then we can end for today. Okay, so essentially we are talking. We just looked at the quality factor. So you can, if you have any loading effects, that is, you have any load attached to it, it is the total queue is called the loaded queue. Or if you are just looking at the particular circuit, the resonator circuit, its queue is called the unloaded queue, and the unloaded queue is given, the expression is given over here. Now, taking a look at the input impedance, if we away from the resonant frequency, so omega naught is the resonance frequency, and the if we take a small delta omega, and which is delta omega is very small, and we're taking the we're looking at the input impedance where at omega, which is a little far away, like with small disturbance to the omega naught. In that case, the input impedance is given over here, and we can just take this omega common, j omega L common, and we end up with something looking like this. And this LC can be written by as omega naught square. Okay, so this is the input impedance expression in terms of omega and omega naught. So omega naught is the resonance frequency. So omega naught is 1 by LC, and now omega, this we can write omega square minus omega naught as omega minus omega naught plus into multiplied by omega plus omega naught, and this thing over here is delta omega, and this thing over here can be written as 2 minus delta omega. So we have removed the omega naught term over from over here. Okay, so maybe did I miss some expression over here? Okay, let's not worry about it. So what we can do is we can now replace this term over here by okay, so there's an equal to, and so there's some steps missing over here. So we can write this particular term as delta omega 2 omega minus delta omega square. Now if this delta omega is very small, we can just ignore this term over here, and we'll end up with delta omega 2 omega, which is so over here, 2 omega delta omega, and then we can just substitute this value back to this expression over here. So we'll end up with r plus 2j omega j 2l delta omega, which, and this omega square will yeah, so we'll cancel this omega square term over here. Okay, so maybe I'll just write it over here. So r plus j omega l 2 omega delta omega divided by omega square. So we'll just cancel this 2 omegas by delta omega square, and r plus j l 2l, yeah, 2l delta omega. And now this particular thing can also be written as 2r plus q naught delta omega by omega. So okay, so there is some steps missing over here. Maybe you can refer to Podzar or just trust me. So we can write this ls rq naught by omega naught. Okay. So essentially, we are ending up with this input impedance looking like this, and this is an alternate form. Uh, this is an alternate form. You can refer to Podzar for this. Okay. So these are the two ways in which you can write the input impedance in terms of the slight disruption. So just away from the input impedance. Now coming to another important thing, which is called the half power fractional bandwidth. So this is the relationship of between Z input impedance and R, right? So we can plot this relationship over here. If we just take the mod value, so the plot will for a series RLC, it will look something like this. And what happens is if you look at the expression for power, so at input impedance at Zin equal to 2 Zin square equal to 2R2, the average real power delivered to the circuit will be one half of the delivered at the resonance. Okay, so I think the power, yeah, the power is equals to something half I think Zi square, right? V square by R. Right? It is V square by R, right? So V square by Zin. Maybe I'll write this over here. Pin is equals to uh, V square by Zin, right? And if this becomes 2R, so this will the power delivered will be half. So when for half, when power delivered is half, this will happen at R by 0.707. Okay, so this particular thing is the bandwidth, and this bandwidth can also be written as delta by omega, delta omega by omega naught. So, so once we so if you just take a look at this expression over here, so this expression over here, we are equating Zin equal to 2R square, and if you solve this, you will end up with bandwidth equal to 1 by quality factor. So this is important. So you can take a look at the derivation over here at Ozar. A few I've skipped a few steps. So if you face any difficulties, you can let me know. So this is very straightforward. That this is the maximum power is received at the resonance frequency, and at some delta value over here or delta value over here, we will receive half power of the which is received at as compared to the power received at resonance. And this particular bandwidth of the frequency where uh, here we are receiving the half power. This is referred to as the half power fractional bandwidth, and we can calculate it, and this will turn up to be 1 by Q naught. So any questions from this? Otherwise, we'll end today's class. So today we covered this quarter wave transformer, the single stub, and series resonant circuits. The next class we'll look at the parallel resonant circuits. Okay. So if no questions, we can end today's class, and maybe I'll try to schedule an extra class this week so that we can quickly cover up the material. Okay, then I'll stop the recording now.